This is a free response question from 2016. It was question number 2. There's a copy of the free response question and the scoring guide in the Schoology folder. So when we look at this part of the problem, this whole section, part A, was going to be worth 4 points. So we're going to go through this question and answer the questions as we put forth in the last video, but we are going to do some of them in a little bit different order because the order was not hard and fast. It's just a guide to make sure you pretty much cover everything. So with this, we have a new kind of toy ball that's advertised to bounce perfectly elastically. Now, if you remember, perfectly elastic was something we talked about in conservation of momentum. But the defining characteristic of a perfectly elastic collision was that kinetic energy is conserved. We don't have a change in kinetic energy. So right here, this tells us that we're going to be doing either momentum or energy. So it bounces perfectly elastically off hard surfaces. A student suspects, however, that no collision can be perfectly elastic. The student hypothesizes. Remember, as soon as you see this, that is where they are setting your task. The student hypothesizes that the collisions are very close to being perfectly elastic for low-speed collisions, but that they deviate more and more from being perfectly elastic as the collision speed increases. So what is our task going to be? We are going to figure out whether we have a perfectly elastic collision at low speeds. So is kinetic energy conserved at low speed collisions? Or in a low speed collision. And then is kinetic energy not conserved at higher speed? Those are really the questions that we are going to be looking at. Now, since I'm really looking at kinetic energy, I think I'm probably going to use conservation of energy. Now, can you use something else? Absolutely. There are ways that you can do this as with conservation of momentum or impulse of momentum. They are a bit more difficult, but it absolutely can be done. This question for readers who were scoring these became what they called the black hole question because there were just so many possibilities that it just kept sucking in other readers to get all of these graded. So I'm only going to be able to really cover one of the possible answers. But if you come up with something else, as long as it meets the conditions in the scoring guide, you can still get full credit. So when I go through this, what I want to think about is how am I going to figure out the change in kinetic energy? Well, what I want to look at is how the kinetic energy is before the collision and what's the kinetic energy like after the collision. So that would mean that I'm looking at 1/2 mass times my initial velocity squared, and it needs to be equal to 1/2 the mass of my final velocity squared. Now I could use a motion sensor to do this, but I also need to make sure that when I'm doing this, how am I going to make sure that I can control my speeds? If I'm just throwing the ball at a wall or rolling the ball towards a wall, it's difficult for me to make sure that I'm always using the same force to generate the same speed, or the same final speed. So one of the things to me is that this tells me that in order to make sure I'm always correctly getting a controlled velocity, I'm going to use a different part of conservation of momentum. And this is where I'm going to start with my procedure. I'm going to drop the ball. Because if I drop the ball, I'm going to have my gravitational potential energy that is going to convert to kinetic energy. And I can control my height, which will control my initial velocity. Well, once it bounces, my final velocity is then going to convert back into gravitational potential energy, or a final height. So rather than worry about doing my velocities, these are easier to control and easier to measure than my velocities. So the equation I'm going to use is going to be mass times gravity times my initial height is going to be equal to mass times gravity times my final height, which of course these are going to cancel. And honestly, I'm just looking at the heights. This is what I'm going to use to determine whether or not kinetic energy is conserved. I expect this relationship to exist for a perfectly elastic collision, which means that when I'm looking for this relationship, I expect to have a slope of 1. So what am I going to have to measure? Well, the only variables I have are height. So the only thing I need to measure are the initial height and the final height. So I'm going to use a meter stick to measure my initial height, to measure the drop height. And the same meter stick to measure the bounce. Now, the one other piece of equipment that I would like to use to do this, to make it more accurate, is I would like to record the experiment on video to determine the bounce height. It's just going to make it easier because it'll make it more accurate to see, because if I just estimate it based on what I see, I'm more likely to be incorrect. So my procedure, I am going to attach the measuring tape to the wall. It could be meter stick, measuring tape, whatever. That's a P. And then I am going to drop the ball from 5 to 10 different heights. Just pick a number, but you want enough data points. And then I'm going to use video to record the bounce heights. And then I'm going to repeat each drop 3 times. And take an average. Of the bounce. So with this, the 4 points, this whole thing, parts 1, 2, and 3 are scored together. So you get a point for an overall plan in which quantities are measures that could be used to compare mechanical energy before and after a collision with a hard surface. For a conceptually plausible plan to measure pre- and post-collision positions without extraneous equipment. So again, if you say that you're going to use something, make sure that you do it. You show it in your procedure. For having lab equipment and measurement procedures well specified, you get a point. And for a procedure that includes trials of different pre-collision speeds. So this is where you do from different heights. So these grading instructions are very vague because, again, there are so many possibilities. And I think in the scoring guide, they have a couple of different options. So if you look through that, you can find some of the other options that were available. All right, so for this one, for data analysis, we want to describe how you would represent the data in a table or a graph and explain how that representation would be used to determine whether the data are consistent with the student's hypothesis. So we're going to do a graph. And what we're going to graph is we're going to graph that initial height, final height question. But I want to turn this into my line equation. So I want to put this in the form of y equals mx plus b. So what I am changing is my independent variable. That is my x variable. I am changing my initial heights. So x is going to be my initial height. What I am measuring is the dependent variable, which is the y variable, which is my final height. My slope is what relationship I'm looking for. In a perfectly elastic collision, I am looking for a slope of 1. So this is what I'm going to graph. And then if it's a 1, I'm going to have a perfectly elastic collision. If it is not 1, or if it's not elastic, then I expect my slope to be less than 1, because if it's more than 1, it's going to be getting energy from somewhere else. So I'm going to explain how I'm going to represent my data, because that's what the question is asking for. I don't actually have to do it, I just have to explain it. And I am going to graph h naught, which is my initial height. Make sure you define your variables on the y-axis. And h final, that's the bounce height, on the x-axis. And then if it supports the student's hypothesis, or to support, at low speeds, the line of best fit should be close to 1. Or slope of 1. At high speeds, the data points should drop below that line. So that would be an explanation of how to analyze the data. And this is also worth 4 points. 1 for describing how to plot or represent the data. 1 for describing how to compare the post and pre-collision mechanical energy. And when I said or suitable proxy in the original video, this is what I meant. Suitable proxy means that I am not actually doing the velocities. I'm plotting height instead of velocity. My height is a proxy for the velocity that I've shown through my equation. I get a point for comparing the low speed versus high speed results, and a point for addressing the hypothesis with an analysis such as slope, ratio, or difference. All right, the last part is the what if section. So this one says that a student carries out the experiment and analysis is described in A and B, and then immediately concludes that something went wrong in the experiment because the graph or table behavior shows that we have elastic for low speed collisions, but it appears to violate a basic physics principle for high speed collisions. So we want to give an example of a graph or table that indicates nearly elastic behavior for low speed collisions, but appears to violate a basic physics principle for high-speed collisions. Well, if I do my graph, we said that we were doing the final and the initial. So at low speed, that's when we have a short initial height. So here I should have a line that's approximately a slope of 1. Now, at higher speeds, we're violating a physics principle. Well, the physics principle that we did was conservation of energy. And the only way that conservation of energy is violated is if we either create or destroy energy. Well, destroying energy just means that it could have gone somewhere else. So that doesn't necessarily mean we're violating a physics principle. Creating energy, on the other hand, would definitely violate a physics principle. So how could we represent that on the graph? Well, that means that our final height is going to be bigger than our initial height. So this would represent a violation because instead of continuing on with our one-to-one, we're creating energy here. So this would be a graph that fulfilled that question. The next part is state one physics principle that appears to be violated. So basically, what is it that you did on this graph? And we violated conservation of energy. So the graph violates conservation of energy since it shows an increase in energy after the collision. Now, was conservation of energy actually violated? No, most likely what happened is that as the students were dropping the ball from higher heights, they gave it a little bit of a downward force as they dropped it, or it could be as it bounces back to higher heights, the angle makes it look like it's gone higher than it is. So there's several different ways that this could have happened, and it's not that physics was actually violated. So this was also worth 4 points, 2 points for drawing a graph that shows the low speed collisions are nearly perfectly elastic, and then drawing something that violates physics. Again, all of these are very, very vague because there's too many different possibilities on how this could have worked. And then the second part, you get 2 points for a correct description of what part of the graph shows a violation, and then an explanation of why that representation shows a violation.